Great to see you in this new video, this new presentation. We're still talking about induction and recursion, and now we're going to look at proofs using the well-ordering property. The well-ordering property is a very important property of integers, and we're going to see that we can use the well-ordering property also to prove recursions and replace inductions by this. Now, when we look at the well-ordering property and proofs, it's, like I said, a very important property, and we already used it before to prove certain statements. Now, the well-ordering property or axiom states that every non-empty set of non-negative integers has a least element. So every set that we are looking at, which is composed of non-negative integers starting from 0, which is the lowest non-negative integer, to whatever integers we have, always have a least element. Now, it doesn't have to be 0, it can be a different element, but at least there is one least element in that set. Now, when we are going to use the well-ordering property, we can use it to prove certain statements. And we will see that we can use the well-ordering property instead of the mathematical or the strong induction, and that the proofs are in fact valid in all other conditions. Now, it's equivalent with mathematical and strong induction, so we will have another way to prove certain statements. Now, we will consider some proofs, and in those proofs we will show that the different proof methods are really equivalent. The first proof that we're going to look at is the division theorem. We already have proven the division theorem before using induction and other techniques, but we are going to see and prove this again. Now, what is the division theorem? We've seen it in some previous videos. You can find it again if you want. But in order to be sure that you get what the division theorem is about, I will restate the division theorem here. So when we have an integer a and a positive integer d, then we have unique integers q and r. Q is the quotient and r is the remainder, where we have the remainder between 0 and the divisor. D is the divisor. R can be equal to 0 when the remainder is equal to 0. It means that a is a multiple of d. So basically what we can write is that any integer a can be written as the divisor multiplied with a quotient plus a remainder. That's the main theorem that we have defined before. Any integer can be written like this. Now, we consider a set of non-negative integers from the form a minus dq. So basically we are looking at the remainders, and the remainders are always positive. And the set is based or is composed of a minus dq, where a minus dq is larger or equal than 0, and q is an element of the integers. The set is not empty because minus dq can become as large as possible. So basically we can find any possibility, we can find a large number of elements of this set. Now, by the well-ordering property, the set has a least element, and that least element is r is equal to a minus dq0. So the dq0 is the lowest quotient that we can find. Now, consider the numbers a equal to 35 and d is equal to 8. Using the division theorem, I can say that 35 is equal to 8 times 4 plus 3. So 8 is the divisor, 4 is the quotient, and 3 is the remainder. And what we can now do is to write this set, and this set of a minus dq is equal to 3, 11, 19, 27. So we always add 8 to the lowest number. And basically we see here that we have a lowest number, a least number in this set. Now we have to prove that this is valid for all possibilities, for all A, D, Q, and R. And we also have to say that R is non-negative and R is smaller than the divisor. So these are elements that we have to consider. Now what we have to do, first of all, we have to say that there is the existence of a solution. Can we find a solution? So basically, the proof is based on two elements. First, is there a solution? And second, is this a unique solution? So first we look at the existence proof. And for the existence proof, we are going to use the well-ordering property. We have to consider two cases. A is larger or equal than 0 with x equal to 0. Then we find A minus D times 0 is equal to A larger than 0. So A is an element of this set. That's the first element. So we have the set A minus D times x and x is an element of z. So we just take A larger than 0, x equal to 0. So this means that we find a solution with x equal to 0, and there is in fact an existence of a solution. So that's already one element for A larger than 0. In the case 2, we consider that A is smaller than 0. Now what we can do here, say that x is equal to A. So basically we can say that A minus dA is A times 1 minus D, and we know that D is larger than 0. So basically we assume in the first step that D is equal to 1, and then we find A times 1 minus D, D being 1, is equal to 0. And when D is larger than 1, we can say that A times 1 minus D is larger than 0, because in our case, we have A smaller than 0. So we're looking at the case where A is smaller than 0. 1 minus D is smaller than 0. So it means that A minus D times A is a positive number, is an element of S. So basically, we find here those two cases to be proven. Now, in those two cases, there exists an element, part of the set, which means the set is non-empty. So that's the first element. We already know that the set is not empty. Now we have to find out, is this the lowest or the least number? Now, we know that the set is not empty, but what about this second element, the well-defined property of that set? So let's have a look at that. We can say the set contains an element. We have the element is R, the remainder is A minus Q times D, and R is larger than or equal than 0. So we know when D divides A, the remainder will be equal to 0. So the lowest number that the remainder can have, since it's positive, is in fact 0. Now we must prove that R is smaller than D, and we will use the proof by contradiction, and we will assume that R is larger or equal than D. So we already know that the remainder has to be smaller than the divisor, but we still have to prove it. So first of all, we can say that R is equal to A minus Q times D, which is larger or equal than D. So that's what we assume now, based on this assumption. So when we bring D to the other side, we have to say that A minus Q times D minus D is larger or equal than 0. Basically, we can rewrite this that A minus D times Q plus 1 is larger or equal than 0. And this is a form A minus D times X larger or equal than 0. But A minus D times Q plus 1 is smaller than A minus D times Q, which is equal to R. This contradicts that R is the least element. So by contradiction, we have shown that R is smaller than A, which is important that we prove this. Now, the next thing to do is to see if the theorem has a unique solution. We know that the solution is the least solution of the set, but is it unique? Now, how do we do this? Well, first of all, let us assume that there are two possible solutions. So we can basically write that A is Q times D plus R, but it's also equal to Q prime times D plus R prime. And R prime are between 0 and D. They can be equal to 0, but they have to be less than D. Now, basically, when we look at this, we can say that basically we want to prove that Q prime is equal to Q and R is equal to R prime. So these are important things that we want to prove, because if Q is equal to Q prime and R is equal to R prime, it means that there is a unique solution. We can write this also as R is equal to A minus QD, and R prime is A minus Q prime times D. With this expression, I can say, when I make the difference of the two, I can say that R prime minus R is equal to D times Q minus Q prime. We multiply the first inequality with minus 1, so it inverses, and it writes minus D is smaller than R, which is smaller or equal than 0. So it inverses the inequalities because we multiply the inequality with a negative number. And what we do now is we add it with the remaining inequality. So we add the two inequalities, and I find that minus D is smaller than R prime minus R is smaller or equal than 0, which also means that the absolute value of R prime minus R is smaller than D. And that's the element that we are going to use to prove the uniqueness. Now, we had already proven, or we had already found, that following the conditions that R prime minus R has to be smaller than D, or the absolute value has to be smaller than D, than the divisor. So now we can calculate the absolute value of R prime minus R, which is equal to D times Q minus Q prime. And this gives that the absolute value of R prime minus R, and we change or replace R prime minus R by the value that we just found, by dq minus q prime. So we find that the absolute value of R prime minus R is equal to the absolute value of d times q minus q prime, which we can rewrite as the property of, in fact, the absolute values, that the absolute value of a product is equal to the product of the absolute values. So I can say that the absolute value of D times absolute value of Q minus Q prime is smaller than D. Now, we already know that D is a positive number, so the absolute value of D is equal to D, and we can divide, in fact, after this, when we have this equation, we can divide it by D, both sides by D, and I find that the absolute value of Q minus Q prime is smaller than 1. Now, based on this, we also know that Q minus, or the absolute value of Q minus Q prime, is between 0, can be equal to 0, and 1. Now, based on this, Q minus Q prime, or the absolute value of it, is an integer. And we have to have an integer which is smaller or equal to 0, but smaller than 1. Now, it means that the difference of, or the absolute value of the difference of Q minus Q prime has to be an integer smaller than 1. And the only integer that we can have is 0. So Q has to be equal to Q prime, which means that also, in order to keep the equality of the original expression, that R also has to be equal to R prime. So basically, this proves the uniqueness. The first part of the proof was done using the method of the well ordering of the set. So we have proven two things. First of all, the set is not empty. And the second element that we have proven is that the solution is unique. The uniqueness of the solution, we didn't use the well-ordering property there, but basically it's very important to prove both elements, the existence of that element, of a least element, and proving that the least element is in fact a unique solution. Now we are going to the next session where we look at recursive definitions and structural induction. We continue with this chapter. You're doing a great job, and we will continue in the next video. Thank you and bye-bye. See you there.